My name is Ming Fu, from a PhD student from Huazhong University of Science and Technology. Today I'm going to talk about how to accelerate restore and garbage collection in deduplication systems while exploiting historical information. This is a joint work with researchers from Huazhong VCU and the National Engineering Center of Parallel Computer. Data duplication is a scalable compression technique. It has become one of indispensable features in large-scale backup systems. Different from traditional compression techniques that compress a piece of data at byte granularity, data duplication compresses the entire storage system at chunk granularity. Previous work have shown that this trade-off can detect more redundant data. However, one of the biggest problems of data duplication is the fragmentation problem. Its negative impacts are twofold. First, the fragmentation decreases the restore performance. Since the data we need is dispersed physically, we observe a 21 times decrease of restore performance in our data sets. Second, the fragmentation decreases the efficiency of garbage collection, since the data we do not need is also dispersed physically. I would like to use an example to show how data duplication works and how the fragmentation arises. Here is the initial backup happens in the first day. Data duplication divides the backup stream into non-overlapping chunks and assigns each chunk a fingerprint. Generally, the fingerprint can be SHA-1 digest. However, in our case, we use a character instead of SHA-1. Two chunks with an identical character are duplicate. As shown in the figure, the first backup stream consists of 13 chunks, and since the storage system is empty, most of them are unique. Exceptionally, the chunk A and the chunk D appear twice. In the storage layer, all the unique chunks are aggregated into containers that are larger units than chunks. Containers generally can be several megabytes, while chunks several kilobytes. In our case, we suppose each container can hold 3 chunks. If we need to restore this backup stream, we read the chunks according to the fingerprint sequence called a recipe. For example, the container is our prefetching unit. For example, we need to read the chunk A at first, so we prefetch the entire container 1 that is holding the chunk A into the in-memory LRU restore cache. Suppose our cache is 3 container size the LRU cache. We need to read 5 containers to restore the complete backup stream. And if our cache is unlimited, we need to read only 4 containers to restore this backup stream. In the second day, our data is changed a little. For example, the chunk B is changed to chunk L. The second backup stream also consists of 13 chunks, and 9 of them are duplicate. The 4 unique chunks, L, M, N, and O, are aggregated into 2 new containers, 5 and 6. This time, if we restore this second backup with a 3 container size LRU cache, we need to read 9 containers. And even with an unlimited restore cache, we need to read 6 containers. That is much slower than restoring the first backup. This is because the fragmentation arises. And after our second backup, we delete the first backup. And the 4 chunks, B, F, H, and K, become invalid since the second backup doesn't reference them. However, we cannot reclaim their space without additional mechanisms. For example, we try to reclaim the chunk K in the container 4. However, the chunk J in the same container are still referenced by the second backup. We fail. We can use an additional container merge operation during garbage collection that migrate valid chunks into new containers. For example, during garbage collection, we can read the container 3 and 4 and copy the chunk G, I, and J into a new container 7. However, this operation triggers a lot of IOs and becoming the most time-consuming phase in GC. We observe that the fragmentation comes into two classifications: sparse containers and out-of-order containers. A sparse container is of utilization smaller than the utilization threshold. For example, the container 4 has only 1 chunk referenced by the second backup, so its utilization is 1/3. That is smaller than the predefined utilization threshold, for example, for 50%. Hence, the container 4 is a sparse container for the second backup. An out-of-order container is accessed intermittently. For example, all the 3 chunks in the container 5 are referenced by the second backup. However, the 3 chunks are accessed intermittently. So the container 5 is an out-of-order containers for the second backup. Sparse containers and out-of-order containers have very different negative impacts. Sparse containers directly amplify the read operations and hurt both restore and garbage collection. A potential solution is to rewrite referenced chunks in the sparse containers to new compact containers during backup, namely rewriting algorithms. Out-of-order containers only hurt restore performance, hurt restore performance only if the restore cache is small. So a simple solution is to increase the restore cache. We also can develop a more intelligent replacement algorithm than LRU. I will use an example to show why existing rewriting algorithms cannot solve the problem caused by sparse containers. Existing rewriting algorithms uses a rewriting buffer to hold consecutive chunks during the backup. As shown in the figure, in the third day we backup this stream, and currently the rewriting buffer holds 6 chunks from E to J. The 6 chunks are all duplicate. While analyzing their container IDs, we find the chunk M has no physical neighbors in the rewriting buffer. And as a result, the existing rewriting algorithms will identify the chunk M as in a sparse container and rewrite it into a new container. However, if we extend the rewriting buffer to hold more chunks, we can find more physical neighbors of the chunk M, including L and N. This time we find the chunk M is in an out-of-order container rather than in a sparse container. We can use an extremely large rewriting buffer to hold the entire backup stream, and then we can identify all sparse containers. However, this method is not scalable since memory is limited. So in summary, the problems of existing rewriting algorithms is that they cannot accurately differentiate sparse containers from out-of-order containers due to limited size of the rewriting buffer. As a result, they lose too much storage efficiency and gain limited restore speed. The challenge is that due to the existence of the out-of-order containers, accurately identifying sparse containers requires the complete knowledge of the ongoing backup. How can we obtain such knowledge on the fly? Due to the incremental nature of backup workloads, consecutive backups share similar characteristics, including fragmentation. In order to observe the potential characteristics of sparse containers, we analyze 3 datasets, and we have 3 key observations. First, the number of total sparse containers in each backup continuously grows. It indicates the problem caused by sparse containers become more severe over time. Second, the number of total sparse containers increases smoothly. It indicates in each backup we have only a limited number of emerging sparse containers. An emerging sparse container is not sparse in last backup, but becomes sparse in the current backup. Third, a backup inherits most of the sparse containers of the last backup. It indicates a sparse container remains sparse in the next backup. So inspired by these observations, we develop a deduplication system as shown in the figure. We have a fingerprint index, a container pool, and collected historical information on disks. And the colored module are our contributions, including a history-aware rewriting algorithm used in backup to solve the problem caused by sparse containers, and abilities optimal replacement algorithm used in restore to solve the problem caused by out-of-order containers, and a container marker algorithm used in garbage collection as a new reference management approach to reduce the metadata of garbage collection. History-aware rewriting algorithm is simple. HAR monitors the utilizations of all containers during the backup and records the container IDs of all sparse containers after the backup. All the referenced chunks in the sparse container will be rewritten during the next backup. In such a scheme, the emerging sparse containers of a backup become the inherited sparse containers of the next backup. HAR has at least 3 advantages. First, do not rewriting emerging sparse containers doesn't hurt restore performance due to the limited number of emerging sparse containers. Second, rewriting inherited sparse containers doesn't hurt backup performance due to the limited number of inherited sparse containers. Third, HAR identifies sparse containers accurately since a sparse container remains sparse in the next backup. HAR has solved the problem caused by sparse containers. However, out-of-order containers still hurt restore performance if the restore cache is small. Our key observation is that we restore backup string according to the fingerprint sequence preserved in the recipe. As a result, we exactly know the future access pattern of containers during the restore. So a more intelligent cache replacement algorithm than LRU is possible. We implement the Bialyd's optimal replacement algorithm in our system. When the restore cache is full, the container that will not be accessed for the longest time in the future is evicted. Garbage collection in deduplication systems is complicated since each trunk can be shared by different backups. GC is two-phased. At first, we need a trunk reference management approach to find all invalid trunks and calculate the utilizations of the containers to identify sparse containers. And the overhead is proportional to the number of trunks in the system. Second, we need a container merge operation to migrate valid trunks in the sparse containers to new containers. This operation competes with regular backup and the urgent restore for I/O bandwidth and becoming the most time-consuming phase in GC. Our observation is that HAR has reduced the sparse containers, and each rewritten sparse containers is irrelevant to later backups. So after the latest backup referring to the sparse container is deleted, we can directly reclaim the container rather than merging it. We don't need to. We no longer need the container merge operation, and we no longer need to calculate the utilizations of containers. And so a simpler reference management approach is possible. We develop a container marker algorithm. The algorithm maintains a container manifest for each data set. The manifest records IDs of all containers related to the data set, and each container ID is paired with a backup time that indicates the most recent backup referring to the container. Suppose we delete all backups before time t. All containers in the manifest recorded in the manifest with a backup time smaller than t can be reclaimed directly. So the overhead of this reference management is proportional to the number of containers rather than trunks. In order to evaluate our ideas, we implement the baseline that doesn't rewrite any data and two existing rewriting algorithms, CBR and CAP, for comparisons. We use three metrics. First is the deduplication ratio that is defined as the size of the non-deduplicated data divided by the size of the deduplicated data. Deduplication ratio indicates how much data we write to the system. Second is the speed factor. It's a metric to measure restore performance. It defines as the size of restore data in terms of megabytes per container read. A higher speed factor indicates we restore much more data per container read, so we can read less containers to restore the same amount of data. And so we a higher restore performance. The third metric is the number of valid containers to measure the actual storage cost after garbage collection. We use three data sets. VMDK comes from a virtual machine. Linux is downloaded from the web. Synthetic is a synthetic data set. Here are the default settings in our evaluations. The default container size is 4 megabytes. The utilization threshold in HAR is 50%. The default backup retention time is 20 days. It indicates at any moment we keep the 20 latest backup. We don't apply the container merge operation. This figure compares the deduplication ratio between rewriting algorithms. Since the baseline doesn't rewrite any data, it achieves the highest deduplication ratio. Since HAR identifies the sparse containers more accurately, it doesn't rewrite any out-of-order containers. It achieves a significantly better deduplication ratio than two existing rewriting algorithms, CBR and CAP. The result indicates HAR rewrites less data than CBR and CAP. This figure compares the restore performance. And showing the figure, the restore performance of the baseline decreases over time. If we use the the optimal cache can improve the restore performance by a factor of 2. However, its performance remains very poor. CBR and CAP can further improve the restore performance based on the optimal cache, and HAR achieves the best restore performance in the two data sets. The results indicate HAR achieves better restore performance while rewrites less data than existing rewriting algorithms. This figure compares the restore performance on the various cache sites. When the cache is small, out-of-order continuous are dominant, while when the cache is large, the sparse continuous are dominant. Since HAR aims to reduce the sparse continuous, it achieves significantly higher restore performance when the restore cache is large. A large restore cache in backup systems generally is not a problem since restore operations is rare and critical. Users restore their data only when they lose data. This figure compares the storage cost after garbage collection. Also, at any moment, we only keep 20, the latest 20 backups. The storage cost of the baseline increases over time. It is because the problem of sparse continuous become more severe. Because HAR reduced the sparse continuous, it achieves a significantly lower storage cost than the baseline. Since the presentation time is limited, I cannot present all of our work. You can find more in the paper, including a hybrid rewriting scheme. This scheme can combine HAR and existing rewriting algorithm to solve the problem of sparse continuous and out-of-order continuous together, and more experimental results and related work. In summary, we first propose a fragmentation taxonomy. Fragmentation can classify into sparse continuous and out-of-order continuous. And then we propose a history-aware rewriting algorithm to solve the problem of sparse continuous, and an optimal cache to alleviate the problem of out-of-order continuous. And finally, we develop a container marker algorithm as a new reference management. It has significantly lower metadata overhead than existing reference management. Thank you.
Hello, Philip Shalane from EMC. I thought it was very interesting. In your garbage collection technique, you keep track of when containers were last referenced, which daily backup referenced which containers. So what happens when you have to do a merge operation, a copy forward data and merge containers?
You mean the merge operation?
What's the interaction between the merge operation and your garbage collection algorithm?
During garbage collection, the merge operation will read the sparse containers and copy the reference chunks into more compact containers, new more compact containers. And this operation will need the data and the right data. So it's
right, but your garbage collection depends on keeping track of when containers were referenced. And when you perform the merge, you merge two containers with different reference histories together.
The merge version triggers a lot of IOs and is the most time-consuming phase in garbage collection. And in our scheme, we don't need to merge any data containers, so garbage collection is very efficient.